Okay, good morning to all. It's a good Wednesday, and I know 8:30 class is difficult. Okay, it's fine. Okay, we don't let the time affect us. And I'm going to teach today, and we are going to go into shear stress distribution equation. Okay, so we don't just find a magnitude. We're also going to write down the equation. Okay, and then on 4th of February, there will be lectures from 8:30 to 9:20, and then 10:30 to 11:20 again lectures. Okay, and as you can see, I've been lecturing even though it's tutorial. I still lecture and do examples at the same time. Okay, right. So we're going to continue our example. The last time where we stopped, just to quickly recap. Last Monday, I show you how to get more important is I showed how to apply the rules, the law. Okay, rule number 1, rule number 2, number 3, 4, and 5 to solve problems. Okay, with these rules, the problem looks simpler. Okay, so what we have done on this example, we have found stresses at point A. Okay, and I shift off a bit. Okay, I shift off in the sense that we start looking for forces, or sorry, stresses at the centroid. Okay, and I think a big thing of what you learn on Wednesday is whether you take the first moment of area from the bottom or from the top. The answer will be the same at the centroid. Okay, because at the centroid, neither of the area, either from the top or from the bottom, will cross over. The first moment of area will not cross over the centroid. So you can either take from the top and from the bottom. And it's so obvious for this case, you take from the bottom because you can see that the equation, right? The equation over here, okay, the equation over here is so much simpler. Okay, less components, right? Whereas if you take from the top, there's a lot. Okay, so you make your choice. Okay, so I'll usually use easier geometry because less mistake will be done. Okay, and important to take note is the first moment of area, whether from the top or from the bottom, is the same. Okay, I want you to have that confidence. Okay, because it can be confusing at times. Once you are confused, you some usually what I realized about like myself when I was young, when I lose the confidence, okay, I lose the objective of the learning of attempting the question in the exam, and I lose marks. I don't want you all to have that experience at all. Okay, I want you all to have that comfort level. Okay, that's why those homeworks are all about. Right. So there's another point to find. Okay, the point to find that we're going to do now is to find shear stress. Okay, shear stress at point B. Okay, so now we're going to go determine the shear stress at point B. Okay, shear stress at point B. So again, first moment of area, first moment of z-axis about point A is go to A, y bar, right? So what I usually like to do is I like to go with depth, then I do y bar. Okay, so is this area now? Okay, we have to consider. Okay, and then I'm going to sketch out the centroid. Okay, sorry, there's the centroid. I've just drawn in green. And the distance, okay, this distance is 65 millimeters. Okay. Because from the top is 35, the entire height is 100, so it's 65. Okay. So we find the first moment of area because there's two webs, one on the left, one on the right. You multiply by 2. Okay. And then the width is equal to 0.02. The depth is equal to 0.03. And then the distance is equal to 0.065, the y bar, okay, 0.065 minus by 0.03 divided by 2. Okay. So where this is this distance from here to here. That distance over there. So you can see that distance is so over here. This distance over here is equal to 0.03 divided by 2, right? And then the whole thing is 0.065. Okay. Now, why I like to use width multiplied by depth. Okay. So when I calculate y bar, I know I need to use this value. Okay, so this value immediately come to here. Okay, so that's why I always go with multiply by that multiply by y bar for that reason. If some of you are curious. Okay, so the 2 over here, as you can see, this is due to the left and right web. And just to let you to recall, this is usually known as a flange. And this is usually known as a web. Okay. So your first moment of area, so we will calculate, is equal to 0.065 minus by 0.03 divided by 2 times by 0.03 times by 0.002 times by 2 is equal to 60 times 10 to the power minus 6. I'll do it again, okay? 0.065 minus 0.03 divided by 2 times by 0.03 times by 0.02 times by 2. Yep. Okay. So from here, right, we now know that the shear stress in XY at point B, right? So we apply the 5 rules. V and I are constant regardless of point of interest, regardless. Okay, so you get 90 times 10 to the power 3. And then your I is equal to 5.813. 3 times 10 to the power minus 6. And then your first of moment of area is 60 times 10 to the power minus 6. And then you need to divide by 2. Again, this is due to left and right web. And then the thickness is 0.02. So this is equal to 90 power 3 times by 60 power minus 6 divided by 5.8133 power minus 6 divided by 2 divided by 0.002 is equal to 23.222 times 10 to the power 6 Pascal. Okay. So that is the how we determine the shear stress at point B. Okay. So now we are looking at specific points. What if we want to look at the distribution? If we want to form the distribution of the shear. Before I carry on, any burning question that you have to ask, please do so. Anyone, please.
Yeah, I actually have a quick question.
Yes.
Just because it's kind of been a while since I've like really thought about it. The like the shear XY, that's XY again because we're talking about the plane is the X plane and then the force is in the Y direction.
Okay, I will help you recall. Okay, that's a good question. Look, so this is our XY plane, and this is rotation Z, right? So when we view this, this is our Y, Z, and this is our rotation X. Now, Locke has asked a question that is really, really good, okay? You just need to recall, okay? I don't think it's a thing that is difficult, okay? You just need to recall, okay? So watch this, okay? If now, okay, I were to place an element down here, okay? We place an element. right? So I'm going to draw that element in 3D now. Okay, we're going to sketch that element in 3D. Okay, so this is our X, Y, and Z. Okay, so we draw the element. Right. So we calculate the shear force, right? We calculate the Vy is coming down in this direction. Okay. Okay. So we know the shear stress will come down in this direction. Okay. So we call this shear XY. Why is that? The X is this plane that I'm shading in the blue. Okay. This is the plane, the axis, the plane is intersecting. So if you bring the plane there, the plane intersect the what? The x-axis. Yes or no? So that is what this x is all about. Okay. The y over here is basically the direction the shear force is pointing. So it's in line with the y-axis, right? The shear is in line with the y-axis. That's why I call it y. Okay. And because of equilibrium, we have to have a counter over here. So this is our shear yx. And therefore, the shear xy has to be equal to the shear yx. Luck, is that clear now? Clearer now?
Yeah, thank you.
Okay. And I think you have to get this orientation right, because later on, when we do 3D, okay, this is so critical, okay? You F it up, okay? You don't know what shear stresses are you counting. Okay, good. Right. So next one, we want to calculate, we want to determine the shear stress equation. Okay, and then we are going to apply the 5 rules, okay, when forming this equation. So I'm going to go and get the 5 rules. Okay. I know it's 5. Okay, 5 is quite a lot in some cases. Okay, in a real instance, they use Eugene. Where am I now? Undo. In some instance, they have 10, and they cut it down to 2. Okay, I only have 5. I can't cut any. Okay, so we are going to look at these rules. Okay, and we are going to determine the shear stress distribution equation. Okay, so same question. Okay, everything's the same. Okay, so we want to so we also know that the centroid is over here, right? So the first part is we are going to determine the shear stress equation, okay, of the flange. Okay, so we're going to determine the shear stress. Oh, sorry. Determine shear stress equation of the flange. Why I like to determine the flange first, or we have to determine the flange first, is because the thickness is equal to 0.16 meter. Okay. And then the limit, okay, the limit of this equation, the limit will be 0.015 meters y, and it will go to 0.035 meters. Okay. And some of you say, Eugene, why that's the case? Okay. So I'm going to sketch y. Okay. So now I'm going to sketch the flange